We saw in previous lectures of both Planck's work on blackbody radiation and Einstein's work on the photoelectric effect that understanding the interaction of electromagnetic radiation, or light waves, and matter is very important. Chemists need to have a fundamental understanding of electromagnetic radiation. So in this lecture, let's introduce electromagnetic radiation. The height of the wave, or displacement from its equilibrium, is called the amplitude, or intensity. The wavelength, denoted by the letter lambda, is the peak-to-peak distance of the peaks or troughs in a wave. As you can see here, different waves have different wavelengths. As you can imagine, these wavelengths are reported in length units, typically in meters, nanometers, or centimeters. The wave also has a characteristic frequency, denoted by the letter nu. This represents the number of cycles of the wave per second. Let's bring in our friend Argon to help illustrate. Imagine this frame as 1 second in time. Argon goes from the origin up, down, and back to the equilibrium, representing 1 cycle. Then, Argon goes through another cycle during the 1 second time frame. This is a frequency of 2 cycles per second. Here, Argon goes through 4 cycles per second. And are you ready for our last example, Argon? Argon goes through 8 cycles per second in our last example. The term cycles per second is rarely used as a frequency unit. Rather, we use 1/seconds or inverse seconds. This is equivalent to seconds raised to the -1, or hertz. Another property of electromagnetic radiation is the speed of radiation, or speed of light. The speed of light is denoted by the letter c and is equal to 3.00 times 10 raised to the 8 meters per second. This is rounded to 3 significant figures. It's also interesting to note that this is the value of the speed of light in a vacuum. The speed of light is equal to the wavelength times the frequency, lambda times nu. Note how the frequency and the wavelength are inversely proportional. In this example, I solve for the frequency, which is equal to c over lambda. At higher wavelengths, the frequency is low. Conversely, the shorter the wavelength, the higher the frequency. Now, let's recap. Electromagnetic waves have a characteristic amplitude, also called the intensity, a wavelength, and a frequency. Electromagnetic radiation also has a velocity or speed of light in a vacuum, which is 3.00 times 10 raised to the 8 meters per second, and is equal to the wavelength times the frequency. From the equation and the examples, the wavelength and the frequency are inversely proportional. When one increases, the other decreases. In my next lecture, I'll show you how to use the speed of light equation to convert wavelength to frequency and vice versa. Argon and I thank you for watching. and hope you can join us for the next lecture.